In object co-manipulation, even in the absence of verbal cues, we can infer the intent of the other person. In case of sudden changes in direction, we immediately follow their lead while reflecting constraints and capabilities of both of us. These challenges are not always addressed, even in human-human interaction. Robots, being significantly stronger, can be better assistants if we tackle these challenges. In this work, we focus on human-robot collaboration tasks, with robot being capable of assisting in rotational commands. For instance, when the human requires rolling a heavy pot, robot should reduce the torque on human wrist. In such scenarios, robot needs to be also robust with respect to variable weight of the object. We emphasize the importance of object transport to a goal in full 6D pose and propose a novel intent estimation method while considering constraints for both agent's capability and task feasibility. It is also important to smoothly switch the robot role between a leader and a follower. As leader, robot reduces the effort of the human, being more capable than a human partner. And as the follower, robot will follow the human lead in instances of disagreement. Our method shows 30% better performance than the state-of-the-art. Human intent estimation is a formidable challenge. Here we seek a representation of intent that is approximately accurate and proves valuable for dynamic control. We begin by modeling the human intent as an autonomous dynamical system directed towards a specific goal pose. DS-based controllers are robust to disturbances, and combined with an impedance controller, can be used to achieve force-level compliance. Additionally, task dynamics depends purely on motion history, without relying on force-torque sensors. However, using only DS to model the intent is not sufficient, since it only follows the specific dynamics of motion and towards a predefined goal. In a realistic human-robot collaboration, the dynamics of motion and goal, which are the DS parameters, are unknown. Using particle filters, we use past velocities as observations and use Bayesian update to estimate the probability distribution of the DS parameters. Since we need to consider explicit constraints, we use two filters, one for Cartesian coordinates and the other rotational coordinates. The particle filter uses a zero dynamics model with noise and an observation model to estimate probability distribution of the goal state. The noise represents the uncertainty of the estimation. Intuitively, when the confidence of the estimate is high, a low noise is preferred, so the estimated goal and dynamics stays steady. And when confidence is low, a high noise is preferred for fast changes in the estimation. Based on the estimated states and dynamic matrices, the velocities and accelerations are evaluated. Particles are then scored based on the error with respect to the velocities and accelerations of observation models. We tailor the particle filtering strategy by trimming the remaining particles to also take into account the capability and constraints of both the robot and human. Because human can freely move in workspace, they inherently adjust their posture and movements based on environmental constraints. Thus, human manipulability can be adopted as an indicator of directional preference, capability, and comfort. We capture human posture during collaboration and reshape the noise of the Cartesian DS based on the hand manipulability ellipsoid axes. To address robot capability, we implement a particle trimming scheme to remove goals that are infeasible for the robot based on inverse kinematics. For computational efficiency, we use Kurobo, a GPU-accelerated inverse kinematic solver. Along with the goal pose feasibility, we also want the robot motion to be feasible. To address this, we use a joint limits-aware controller to realize the desired control input. To respect the joint constraints, a repulsive potential will be generated to resist the violations. In addition, for intuitive interaction and perceived safety, robot should be kept in a joint configuration familiar for the human. This can be achieved with a secondary task projected into the null space. Furthermore, the robot needs to adapt its roles by proactively minimizing human effort as the leader, while in instances of disagreement with humans smoothly transitioning into a follower role and relinquishing control to the human. We achieve this by adapting both the noise of the filter and the impedance control gains online. Integrating the suggested steps, we devised a game wherein the human is tasked with moving a weighty object toward a designated goal pose, specified by longitudinal, lateral, and roll angles. Upon reaching the goal pose, the task ends, and the team reverts to the center of the workspace for the next goal pose to emerge. Throughout this process, the robot remains unaware of the ground truth. The graphs show the confidence level and the force torque applied by the human. As it can be seen in the graphs, when human and robot motion is in agreement, the confidence level is high, and the robot leads with a high impedance gain, generating the majority of the forces for motion and deceleration. On the other hand, in cases of sudden changes in human force that result in unexpected deceleration, the impedance gains drops as a result of motion uncertainty, lowering the confidence level. In this case, the robot acts as a follower. The simulation on the top right shows the influence in particles distribution. At instances of disagreement, particles move ahead of the robot, leading the robot to follow the estimated goal. Our proposed approach represents a significant step forward in physical human-robot interaction, promising to extend the application of robots in various sectors by ensuring their cooperative interactions with humans are both safe and effective.